for the time being, let's just go ahead and go over some calculation here. Let me slide my pen. There you go. Okay, so the topic of this chapter, guys, short circuit calculation and overcurrent protection device. Like I told you guys, this will prep you for next week when we'll be doing, you will be doing with me SKMPTW, where we will be doing a short circuit calculation using this software, as well as the coordination, also using the same software, Overcurrent coordination. Cool? So what you're going to see today is just, you know, if you don't have a software, how do you do a calculation? Nobody does it by hand anymore. It's too complicated. Okay, point-to-point method. That's the one that they use, guys. They call it point-to-point method. You go right where the transformer is, coming from Excel Energy, where Brian works. You go to the line side of a transformer, you do the short circuit calculation there, and then you take it from the point where the transformer is all the way down inside your plant, down to every single panel inside your plant. And you do the calculation by finding the short circuit, line to line, line to ground, line to line, line to ground, and line to line to line. They call it three-phase calculation. You're going to see in a second. Short circuit using tables and charts. If you don't have a software SKM, that's how they do it. They use charts, but no, almost all the engineered project, Adam, every engineering firm have a software. Typically SKM, they do all the calculation with it. And again, you guys will be introduced to it next week. Coordination. Coordination, the term coordination, selective system and non-selective system. These are very simple, very simple topic, guys. Brian, if I ask you to go change that ballast energize, which you're not supposed to go, and accidentally the 120 hot touch the frame of that fixture, which circuit breaker should trip? That one here or the main of Dunwoody? That one. If that trips, you have coordination. If Dunwoody's main trips, you don't have coordination. So everybody understand why nice is coordination. Imagine if Brian is changing the ballast on this fixture, and now all of a sudden short it to the ground, and the main of 3,000 amp main at Dunwoody trips on a ground fault. That's bad news. Imagine that happening in a hospital. Imagine that happening in a stadium while you're watching your favorite show or favorite play. So that very bad news. So that's why coordination is a big deal. Time current curves, guys, we talked about them yesterday and we'll continue to talk about them today. Every overcurrent protection device have something called time current curve. Very simple. The higher the short circuit mat, the faster the circuit breaker will trip or fuse. That's it. So that's the concept that we're going to be talking about. Compared with actual calculation, there will be slight variance. When you do the calculation, guys, there will be slight variance in the numbers that you do. And when we do it, I don't want to emphasize it too much, doing it by hand, because there's rounding of the numbers and rounding of the impedances and what's not. If you're doing it by hand, it will be reactance, different type of reactance. When you do short circuit calculation, you need to do the following. Number one, the size of the transformer that the electrical utility is giving you, the available short circuit at the line side or the load side of the transformer, the primary or the secondary. You need to know all the feeders, guys, what type of conductors, what type of insulation, what type of conduits, all the motors, what type of horsepower, what type of voltage, the impedance of the transformer, all these. If you don't get the exact information, for example, when you pick THHN, you pick THHW and you put it in PVC instead of EMT, you will get different numbers, slightly different numbers. Did you guys see how important it is? When you guys model the system next week with your friend Chad, you do the modeling of the system, we'll use the exact conduit that we designed, the exact insulation, the exact size, the exact transformer, so we can get as close to the actual number as we can. If you're doing it by chart, you don't have all the scenarios, so you're going to have an approximate value, basically, with some variance. Okay, the short circuit calculation start at the terminals of the transformer. So here's my transformer right here. On the primary side, you start doing the calculation right here. If you take phase A, phase B, phase C, grab a wire, shunt them together, connect them together, bad news, right? And flip the switch. That's your start point. you're going to see, guys, transformers have impedances, and the impedance is the only one between you and that flood of short circuit that coming from Excel energy. For example, if I go short the secondary of the transformer, phase A to phase B to phase C, the only thing that prevents me from that flood of current that coming to burn my building is the impedance of the transformer. The higher the impedance, the more it holds that current, and it doesn't burn me that much. You know what I mean? So the impedance chokes the current that coming from Excel, the transmission lines. The impedance by UL, guys, so they have 10% plus or 10% plus or minus impedance. So if your impedance 5%, then it will be plus or minus 10% because we don't know exactly how the impedance is going to be. So there's a fluctuation plus or minus 10% fluctuation in impedance. Who cares? When they give you the impedance of the transformer, if the impedance is 5%, you take 90% of this 5% and you use it because that's our scenario. Utility companies vary voltage within certain range. Also, another factor, guys, is the voltage. We assume that the voltage is nominal if it's 480, 480. Otherwise, if the voltage is higher or lower, you will have different values of short circuit. Different values of short circuit. The assumption is always the voltage stays at 480. So a lot of variables, and because of all these variables, I want to emphasize the word we will use an SKM PTW, so we can arrive at a value that we feel comfortable about. You know what I mean? Instead of doing it by hand, guys, you might not, if you go do it by hand, you might not find a chart for every single scenario, every single conduit, every single transformer. Softwares, like you're going to know, Brian, you've seen it in the spring, they have thousands of components, library that you can pull from. Every manufacturer of every transformer have data about their transformer in the software. So your chances of arriving at close to the truth number is much higher. So same thing, NEMA and the transformer manufacturer, guys, have a short circuit tables. I'll show you in a second. It tells you if your transformer is 25 kVA and you short it, you're going to get, on the secondary, you're going to get this amount of short circuit. It will allow this amount of short circuit to go through. Obviously, the higher the transformer, guys, the more short circuit that transformer can allow. Where's this short circuit coming from, Brian? It's coming from your company, Excel, right? Because Excel pushing power into your building. To power that building, if you short that building, short the phase to phase, that power has to go somewhere. Where does it go? It's going to go burn your building, basically, instead of powering it. Then after we do it at the transformer, then we go find the calculation point to point at various distances. You're going to see the example that we're going to do at every panel. So short circuit distances. We find the short circuit, guys, at the primary, secondary transformer, at switch gears, at switch cords, load centers. So, like you're going to see with me, Karen, next week, you guys are going to find me the short circuit at the lighting panel, receptacle panel, main panel, and at the meter cabinet, at the CT meter cabinet. So then we find, of course, the three-phase or single-phase, if your system is three-phase with a reasonable. And the method that we use, guys, is called point-to-point method. It has 7 steps. I'm going to show you in a second how you start these 7 steps if you do it by hand. If you do it by software, very simple. You model your system into the software, you hit the button, and guess what happened? Like you guys did visual, exactly like we did visual for lighting. You hit the button and you get yourself a short circuit values, line to line, line to neutral, as well as a three-phase line to line to line. Okay, the values that you can get, speaking of the devil, short circuit can be line to line to line. What does that mean, Adam? You have 3 phases. You take phase A to phase B to phase C, tie them with a big wire, make sure it's big enough, and flip the switch. Phase to phase to phase. That's your cool. That's the worst scenario. That's why we size everything based on the phase to phase to phase. The second one is phase to phase, right? Take phase A and phase B and tie them together, flip the switch. That's typically 85% of this. So, Brian, when we do short circuit calculation, we almost always focus on phase to phase to phase. That's the worst scenario. Phase to phase, if it's 80% of, if you cover the phase to phase to phase, do you think that the phase to phase will be covered? Yeah. You cover the worst scenario, which is phase to phase to phase. So then you have line to neutral or line to ground, line to neutral or line to ground. And typically line to neutral, line to ground, guys, typically it's 25% of the three of line to line to line. 20% of line to line to line. Though it could exceed it to 125 under certain circumstances. And what we do as an engineer, guys, we would limit that one. There's ways of limiting the ground fault to a short circuit value, three-phase short circuit values. So typically, if you assume that 25% or 50% is a good assumption for most of ground faults and line to neutral volts. Like I said, rare, this value will exceed the line to line to line value. Line to neutral, this is, guys, accommodate close to 84% of the faults in your building. So 84% math of the faults in your building is going to be line to ground, typically line to ground. A phase touching the frame of that fixture. So, and typically it's very small, so you're talking about 25 to maybe 50%. So for most of the faults, guys, you can handle them. It's highly unlikely you're going to grab phase A to phase B to phase C, tie them together and flip the switch. That's really the worst scenario. That's your chances, sometimes your chances of having a phase to phase to phase is equivalent to your chances, Brian, driving home and get hit by a drunk driver. And, God forbid, join the Lord. Not just get injured, but join the Lord. So that's kind of but how often this would happen over the life of the building? 50 years, guys. 50 years is a long time, so we have to pay attention to it and to save people, not for today. We talk about 50, 40 to 50 years. So that's why we pay a lot of attention to it, even though it's rare. It could, especially the line to line to line. Okay, we got that one. Here's a couple of values for you guys. There's something called also arc flash. The arc fault. This is probably a nice approximation. Here's your arc fault. The arc fault, guys, is the difference between a bolted fault. You're going to hear a bolted fault and an arc fault. Here's what the difference. There you go. Dirk is here. That's all right. It's cold, man. The difference between a bolted fault and an arc fault is as simple as this. Take phase A and phase B, guys. Tie them together with a bolt. Bolt them together. You guys hear me? Bolt phase A and phase B together. Flip the switch. That's bolted fault. Now, if you don't, that's the bad. Now, arc fault is if you don't bolt them together, just make them touch each other. When they touch each other, there is an air impedance between them, right? The air is going to create some impedance between them, so they're going to arc. So it's not going to be as high, though it will be as destructive or more destructive, because now you start arcing. Anyway, because of this, the arcing value, I want to bring to your attention, guys. So the arc fault will be, if your system is line to line, 480, 89%. The arc that's coming out of line to ground is 38% of the values of the three-phase. Look how easy it is, guys, for a 2-8 system. 2-8 system is nothing. 12%, O2. I know you guys, this is a big deal for you, but if you're working on a 2-8 120 panel, you can see if your short circuit is say 100 amp, your arc, the one that's going to contribute to the arc, is only 12 amps. So it's not a whole lot of arc. So summarize. If you have a panel 2-8 120 like we do, the arc flash is going to be much lower than if the panel was 480. Anybody knows why? Higher voltage pushes more current, more energy. So that's the comparing the short circuit that you're going to get from SKM, guys, to the arc flash. Next week, we're going to be doing arc flash calculation, guys. You're going to see a nice sheet that you're going to do with SKM. The nice thing about the software, guys, it makes it really using it fast, and you know how to do it. In order to understand it, a chapter like this will help you understand it. Will help you understand these. Okay, the rest, guys, So we have this, if you have a short circuit of this value, 40.311, when you did your short circuit, right? A good assumption typically is allowing 25%. So you multiply this one by 1.25, and then you size the interrupting rating of your overcurrent protection device. You size the interrupting rating of your current protection device. That 25% guys allow you future expansion, adding more things to your building, adding more load to your building. Here's the chapter that we talked about, guys. The project Karen that we have. When we did a short circuit calculation, here's what you came up with: 34.725. Right at the terminals of the transformer. When you move down, pull a couple of wires all the way down, and then you do the calculation here. It drops it down to 31, so it dropped like what, 3 or 3.5 K. These are 1,000 guys. These are 1,000 amp, 1,000 amp, 1,000 amp. So the worst scenario for the short circuit guys will be at the terminals of the transformer. The further downstream you go, the lower the short circuit will be, and that's because of the impedance of the conductor will choke the current. Hold it. Impedance of the conductor, the resistor of the conductor will choke the current. So the worst scenario will be right at the terminals of the transformer. Right at the terminals of the transformer. Now, if you do the short circuit calculation right at the, let's just say down at the drugstore panel right here, you're going to find by the time the current goes through all, where's the, goes all through here, all the way through all these cables, it's going to choke. The further away, the longer it will be choking it down, and it will be lower than the 31.3. Okay, so all what you need to know, guys, the further away from the transformer you are, the better in terms of short circuit. The worse in terms of voltage drop, but you have to have the happy medium. There's also, we installed for this project, they installed current limiting fuses, guys. A current limiting fuses, like I said, will limit the amount of energy upon the existence of a short circuit. Who cares? Your equipment will not burn as much. So they're installing a non-current limit fuses downstream and a current limit fuses to limit the energy devices installed in the main switch gears. So if you have a current limit fuses, you will limit the energy, not just interrupt the fault. Okay, when you're doing short circuit calculations, guys, absolutely necessary to determine the available fault current at different points in the power system, at every panel. Fully rated systems, if you have a fully rated system, guys, we talked about these one yesterday, it will be more expensive. The interrupt rating not listed in the available fault current. When you size a circuit breaker to interrupt the short circuit, the circuit breaker interrupting rating must be higher than the available short circuit at that point. That's the key point. You guys are going to see that one too next week. To install series rated, remember we talked about series rated, guys, yesterday. Series rated is when you have two circuit breakers in series with each other, coordinated to take care of business. One of them will be at a higher interrupting rating. The second one will be at a lower interrupting rating. And if downstream available short circuit is higher than the lower interrupting rating of the circuit breaker, the big guy will take care of it. And I'll show you. And we showed you guys yesterday how to do that. What is coordination? Coordination, like I said, take Derek here, go fix that while energized. You're not supposed to do that though. Go change that ballast while energized, right? Accidentally shorted that phase to the frame of that fixture. Which circuit breaker should trip? That one right here? Yep, coordinated. If the main Dunwoody trips, we're not coordinating. Take mat, go inside this panel mat and go work on it, energized. Well, you're not supposed to do that in the first place, but if there are reasons for doing it, there's a couple of exceptions where you can work energized. You're working energized right there inside the panel, guys. Now you're shorted face to face to phase or face to neutral. Which one do you want to trip? The main that feed this panel or the main that feed all of Dunwoody? The main that feed this panel, right? That's a coordination is. Localization of the interruption of power to that faulted circuit. They call it selective coordination. Required on emergency systems. required in an EC code book in emergency systems, legally required standby systems. Um, Derek, Mishad Cooley, and all engineering project, every single engineered project, we run a short circuit calculation and an overcurrent protection coordination studies to make sure we have selectivity. Non-selectivity, very simple. You should write the ballast right here, the main of Dunwoody trips. Now everybody in the whole college wait until the electrician walk and go trip the circuit breaker, reset the circuit breaker. Is that bad news? Do you guys want to, do you see how bad that would be? So that's, they call it non-selectivity system. Non-selectivity system. Needless power outages in areas, what does it do? It provides needless power outages in areas that are not affected. I have a short circuit in this room. I don't want to shut down the power every single room on this floor or even the whole 4 floors of Dunwoody. So that's why coordination is a big deal. We'll talk about this one in the fig here. Okay, so here's a good example, guys, where you have a circuit breaker, a 100 amp circuit breaker. Can you guys see that? And a 20 amp circuit breaker. Now Adam went to change that ballast. That circuit breaker is going to be have a short circuit. The short circuit was 10 times the available, give you a 200 amp short circuit, right? 200 amp short circuit. It's sitting, this one is sitting to trip at interrupt and unlatch at a half a cycle and interrupt at a 1 cycle, meaning open in 1 cycle. The one above it is sit the same way. Can you guys see that? These are the same setting. If they're sitting the same, then when you have a short circuit here, guess what? This will trip and this will trip because both of them will see the short circuit and they're set to trip at the same value, no coordination, and that's what we call it non-selective coordination. Next week, guys, you're going to see it. There's a curve. Instead of looking at this, there's a curve. You have 2 curves. If the 2 curves touch each other, bad news. If the curves, each one of them, if the 2 curves, like I said, touch each other, then we have bad news. Here's a curve of the circuit breaker. Here's my circuit breaker 1 here. Here's a curve of the other circuit breaker. Can you guys see that? If they're touching each other right in this area, this means they will trip at a certain value. That's what the coordination is all about. You don't want these time current curves to touch each other. What does touch each other means? They are set to trip at the same speed for the same amount of current, which is not, it doesn't give you a coordination, full coordination. When you do the coordination, guys, almost all the projects that we do, Matt, we go either use selective, the manufacturer's product, or we have SKM. Every engineering firm has SKM. I'll show you guys next week how to grab all these curves and play with them, make sure they don't touch each other. Good to go. Very easy, very visual. You're going to see when you do coordination, guys, instead of looking at all these tables, you're looking at curves, and the curves are colored, green curve with red curve. As long as these don't overlap, we're good to go at every single point and every single time and every single current. Wherever they touch, bad news. They will trip at this value. And of course, manufacturer of circuit breakers, guys, and fuses always give you a selectivity guide. You'll see a couple of them that tells you, use this circuit breaker with this circuit breaker. We guarantee you they are going to select. They will have selectivity. So help you to do that. So published time current characteristics. The time current characteristic curves, you're going to see it. It's a curve that looks like this. Published current here, time here. And every single manufacturer of fuse circuit breaker provide a curve. Luckily, in the past, guys, they used to play with these curves, put them on graphically. Now, all these curves, you can pull them in the software, put them side by side, make sure they're far away from each other, good to go. So, on an overload condition, guys, typically we don't have problem with the overload condition. If you have a 20 amp circuit breaker and a 100 amp circuit breaker, if you pull from the 30 amps, that one with the 20 amp will trip. So overload condition, guys, typically coordination is not hard. It's hard on a ground fault or short circuit. So overload condition, not a big deal. And you're going to see it later on. So less than instantaneous trip setting, upstream circuit breakers breakers having amps, and we'll talk about these guys when we talk about the non-selectivity and the selectivity of these. So we have look at this one, for example, the same scenario. Look at this. The only thing they change here to get your selectivity, guys, I want to bring to your attention how fast this circuit breaker will trip. It will unlatch. Unlatch means, oh, let's start opening and open completely in one side. Everybody knows what a cycle is in times. A cycle is time. A cycle is 1 over 60 of a second, 1/60th of a second. That's fast. Can you witness an event or recognize an event 1/60th of a second? None of us can. So that's fast. So look how fast. This is 1/60th of a second is going to trip. Now this circuit breaker is going to trip, look at this, 7 to 20 seconds. Oh, this is how fast that compared to this. We make this trip fast at this level of amp. By making it trip fast, this guy doesn't have enough time to see it yet, right? That's how they do the coordination. Make the circuit breakers downstream trip faster at their rated amps than the one upstream. If they trip faster, then they interrupt the current, they open the circuit, then this guy has no reason to trip. So it's like Derek, this guy is waiting. So this guy is waiting and waiting. There's a short circuit condition here. That guy waits. When it starts, if it continues to 7 to 20 seconds, it will trip. But this guy will trip before that. So get your coordination at that particular level. Okay. Selective coordination, like we said, guys, here's your selective coordination. You have a fault right here. Low peak dual element time delay fuse, 50 amps with 100 amp, like a 2-to-1 ratio. Will get your coordination between these two. This fuse is not affected. If you have a short circuit, this fuse will open. The manufacturer of the fuses, guys, typically tell you if you maintain a ratio of 2-to-1 between the branch circuits and the feeders, overcurrent protection device, for the most part, you are good. You will do coordination. You go higher than that, 1-to-1, for example, 100 with 100. It's very hard to coordinate 100 amp fuse with another 100 amp fuse. So what does that mean? If your panel is 100 here, don't pull a branch circuit more than 50 out of it. And then for the most part, you're doing good. Does that make sense? Unless you do coordination, of course. You can do a coordination. Okay, single phasing. The 3-phase motors be provided with running overcurrent protection device. For single phasing, guys, if you have a motor and you lose one phase on single phasing, your motor will continue to run. Will pull a motor running a 3-phase. I lost one phase. Now I will continue to run, except these 2 phases will pull more current now to compensate for the loss of that phase. What does that mean? You're going to burn them. But we have an overload protection, typically in trips. So we have an overload protection that trips. Okay, finish. And if the overload protection does not trip, the fuse will trip. The fuse head of it will trip if it's sizable already. So remember, single phasing meaning losing one phase on a 3-phase system. That's what single phasing is. 1 or 2. 1 or 2. You lose 1 or 2 single phasing that motor. So if you have line-to-line voltage in a 3-phase motors, the fuse and overload will open before motor windings are damaged. So for motors, because they're sensitive equipment, guys, they have a short circuit fuse or circuit breaker as well as a little device that's called overload. The overload will trip you on single phasing or overloading of a motor. The fuse or a circuit breaker will trip you if you have a ground fault or a short circuit. Who cares? How do they know which one to trip first? It's all based on the current. For example, Brian is a motor and he runs at 100 amp. If he starts pulling 150, overload trips. That's overload. If he starts pulling, now he's 100 amp, remember. If he starts pulling 700 amps, 700 amp, that's a ground fault. High amps, that's a ground fault. If he starts pulling 2,000 amps, that's a short circuit. So what does it do? It trips faster on the 2000 amp than 700 amp than the 150 amp. That's it. It just looks at the range of the the range of the current. Okay, so that's all I have, guys, for you. Let me show you a couple of charts I wanted to mention. And again, I can't emphasize that we will be going through that one. Here's how they do the calculation by hand. Let me just emphasize again the steps that they do the calculation by hand, guys. Very simple. If you take the fault right at the secondary of the transformer, right at the secondary of this transformer, right here, secondary transformer, the first thing you need to do find fault at AA, line to line here. You take the full load amp of the transformer is given. You know how to find the full load amp of the transformer. You find your full. Here's my transformer. It's 167 kVA. Here's the voltage single phase. Here's the impedance. All the information about that your transformer. If you take the full load current of your transformer is given as this. Here's your value. See how you've got this information on line to line, AA phase to phase here. You take the impedance, guys, and you take 90% of the impedance. You get you this multiplier. Multiply this multiplier by the full load amp. That's the available short circuit. It's 38.6 thousand amps. So you take the full load current, guys, and divide it by the impedance. Very, very simple. Take the full load current divided by the impedance. That's how you find the short circuit of the transformer. The second thing that you do is find the F factor. Now, if you go down to the C, now we're going to the C level. Any question there about finding the transformer? So you take 167K divided by 240. Then you get this number. That's a full load current. Divided by the impedance, which is 2%. And because UL said, hey, it could be it could be plus or minus 10%. So multiply by 0.9 here. So that's your short circuit right at this value here. Now go downstream to C. This is where now this is calculation here. The second calculation at C. Now I pulled conductors, guys, to find when you pull the conductors, they're going to choke the current. So the way they calculate it, here's at 25 feet of two conductors, 500 kcm, conductors at two, I can't read that one. So we have at 25 feet of two 500 kcm copper conductors per phase, each of two steel raceways. Then 25 feet will choke the current. How much choke the current will come to something called the F factor. That's not the bad F. That's just the F factor. How do you find that factor, gentlemen? Here's the calculation. What's the good news, Chad? The good news is all this next week, guys, you'll be looking at it and say, oh my God, I'm glad we have a software for this. It's like visual. How do you do it by hand, guys? You take 2 times L, length times the current, which is you came here, divided by N, number of runs, C, that's the impedance of the conductor, divided by the voltage. Okay, here is 2, because single phase, 25 is the feet, 38 is this number here, can you guys see that? Divided by 2, because we have 2 runs, can you guys see we have 2 sets? Where did it say here? 2 sets. Multiplied by this number, that's a C factor, that's the impedance of the transformer, you find it from a chart, divided by the voltage. And gentlemen, you got yourself the F factor. And if the F factor is not enough, you have to find the M factor. So how do you do the M factor? The M factor, here's the formula for the M factor. You take 1 over 1 plus the F factor. Does that sound like engineering, huh? So now, here's your F factor, the second M factor. Now, what this number means, you will cut the short circuit here by running 25 feet of 2 runs of 500 down to 85%. Choke it. Down to 85%. Okay, then you take the 85%, guys, multiply it by the available short circuit here. And now your short circuit right at this point was knocked down to 32.8 from 38.6 by only 25 feet of runs of cables. It chokes it. Chokes it. Okay, if that's not enough for you, gentlemen, let's go back to another EE. EE is right here. Here's my EE, right at this point. Now I'm going to go, here's my EE. Let's go do the formula again. Now EE, I have 20 feet of one conductor number 2. Okay, so when you guys do that, 2 times 20 feet times the impedance here, divided by the C factor for this conductor is this number, divided by the voltage. find that will give you the F factor, bring the M2 factor. That will knock it down again to 0.52. So gentlemen, by the time you reach this point, you are sitting at 17 point something, 17.9 thousand M. I can't emphasize. We started with this value, guys, right here. We knocked it down to this value, and we knocked it down again to this value. Welcome to choking the current through the impedance of the through the impedance of the motor. I mean, the conductors. On this side, guys, as they're doing the line to neutral. Line to neutral. If we're going to do the same calculation, you do it line to neutral. They're finding the line to neutral values. So the line to neutral, they assume it's going to be this value multiplied by this. This is your line to neutral. Then they're applying these values, and they're cutting it down to this value, and the same thing, line to neutral, cutting it down to these values. Line to neutral. Any comments, guys? Any questions? You're going to be very thankful that we have a software that does all these. But remember, they're going to hear about the F factor, the M factor. These are the formulas they use the F and the M factor for. So I'll start with the impedance of a transformer. So that's basically it, guys, in terms of, okay, here you go. In terms of, then you find, here's the short circuit right at the terminal transformer, then you find it right here, then you find it at each and every one of these panels. You do the calculation at each and every one of these panels, right here. Can you guys see that? Using the same formula that we did. Imagine doing it by hand. Cumbersome. Short circuit occurs here. This will open. That's the coordination. A few things about the coordination. We talked about the coordination. Talked about that. This is what the impedance, guys, is all about. And finding. Here's your F factor, where you find it based on the impedance. The formula is very clear. If it's three-phase, 1.73. Let me go and how do we rotate this one again? I thought we will be able to. Okay, this is the, can you guys look in your book, please? That's how you find the C factor for motors, for conductors. Can you please look at, here's the 208, here's a 240, 480, 600. You're going to find the conductors right here, guys. Copper wire, and it will tell you only for copper wire, and this will be the symmetrical rated available from 300. If this is for 300 transformer at 2% impedance. If your transformer is not a 300 2 impedance, this value does not get you anywhere. Anyway, so if you take a conductor 500, here's my 500. If you take if you take 25 feet distance and you need a 500 conductor, 500, we have 250. Two sets of where's my two sets of 500? Here's my 500. Here's two sets of 500. You can find I think that's the value 39300. These are the C values that you can get for these transformers from these charts. Luckily, gentlemen, all these information will be pulled through the SKM next week when we pull it. But this chart that you're looking at, it will give you the C factor for different. It will give you, this particular one will give you actually the short circuit. These are the short circuit. It will give you the short circuit values at different distances from this transformer using different cables. So already calculated, but only for one transformer though. This one, guys, will give you the full load, the impedance, and the short circuit for different transformers. So let me show you one good example. If you're looking at a transformer what was the transformer that we use here? Let's just pick a transformer of 500 kVA transformer at 208. The full load current is this value. The impedance is this value. And the short circuit at the terminal is this value, all calculated by the manufacturer. That's not rocket science. You just take the 500 kVA divided by 208, 1.73. That will get you this number. then take this number, divide it by this number, will get you this number. Really nothing. It's a percentage though. Nothing. That's called the short circuit available at the terminals of the transformer, published by the manufacturers. Okay, sorry. Now here's the C factor. The C factor, the impedance of the cable, guys, is also published, so you can use them in these formulas. Let me see the 500, just zoom into a little bit into one of them. Here's my 500 kcm wire. My 500 kcm wire. It's 600, so copper conductor, 3 conductors, magnetic conduits, non-magnetic conduits. We are magnetic conduits, right? 600, and I think that was something. So if you have a 600 amp and a magnetic EMP conduit, 600 volt, that will be the impedance of that cable at this point. So this is called the C factor. Remember that formula talks about the C factor? The C factor for every cable. You plug it into the formula, good to go. Good news, the good news, gentlemen, is you're not using these factors. They have them also for aluminum conductor single phase. So for aluminum and copper. So they also have them for plug-in and feeder and high impedance busways, guys. The impedance for these. So long story short, guys, if you don't have a software, you're going to use that formulas that we did. Find the C factor from here, plug it in. Any comments, guys? Any questions? Any comments? Again, most of you guys will be working for an engineering firm, so you don't have to even worry about this. Why? You can pull all this information from the software. Makes you appreciate it. Here's how they calculate the M factor, guys. A table converting M factor. So if your F factor is this number, your M factor is this. You remember the sine and the cosine tables that we used to have, guys? Most of you are young. You don't find the cosine of all the angles is this, and sine and tan and what's not. Before we have the calculators that can do all this one. So if you want a tan of 55, here's the table that gives you tan of 55. That's similar to this. Why don't we care too much if you work for engineering firms? Because all this number is meaningless. It's behind the scene. The software will calculate it, cook it behind the scene. So this is tabulation. What's the formula that you're using? Not rocket science. 1 over 1 plus F. That's the formula that you're using. So if I tell you find the M factor for 100, you take 1 over 1 plus 100. That will be the M factor. So it's really not a whole rocket science. Okay, coordination. The last thing, here's publishing of these typically guys from the Fuse publishers. They will tell you to maintain a full coordination, you have to maintain the following ratio. For example, if you're using this fuse with this fuse, you have to maintain a 2-to-1 ratio. If you're using this fuse with this fuse, you have to maintain a 6-to-1 ratio. A 6-to-1 ratio. What does that mean? 6-to-1 ratio, this will be 600 amp on this side, circuit breaker, guys. Downstream, or fuse, these are fuses, that downstream, that will be, what did we have? 100, that will be 100 amp. Max. So if this is 100, maximum 100 with 600 we coordinate. Make this is 200, no coordination. So that's what the manufacturers tell you. If you use this fuse, with this ratio, good to go. Don't even call engineer to do the coordination for you. That's what contractors use sometimes. If they don't want to spend the money on doing coordination, they use the tables from the manufacturer. They say, yep, the manufacturer told me if I use this fuse with this fuse, max here, don't go higher than the max, I'm good to go. No, I don't need to do coordination. Stadiums, sport arenas, all these guys require you to do a coordination. But look at them. Here's the load and here's the line, or the feeder and the branch circuit. So that's basically it, guys, in terms of coordination and short circuit. Any comments, any questions? I promise you it will be much easier next week when we use SKM. But please read the chapter. In order to fully understand the software, take it to the next level, Adam, you have to be a fully recognized designer. If that's what you want, you have to do short circuit and coordination, what's not. Comments, questions? I'll let you guys go, and you know that Jerry is coming here in half an hour, so please work on your stuff. He's going to give you one more hour of generator. So why don't you, we'll do some coffee, huh? Matt, what do you think? Energize ourselves? All right, thank you.